valence shell electron pair repulsion, or Vsepr for short. What we're talking about when we deal with Vsepr structures is how the electron geometry around a central atom affects the molecular geometry of the molecule itself. So we're going to subdivide our electron geometries based on the number of paired electrons around the central atom, and from there we'll subdivide into the molecular geometries, which are determined by how many of those pairs of electrons around the central atom are bonding pairs and how many are lone pairs of electrons. So we're first going to start with the electron geometry, which is called octahedral. And it's not called octahedral because there are 8 atoms around the central atom. We'll look at where the term octahedral comes from in a second. But an octahedral electron geometry has 6 pairs of electrons around its central atom. And we have several molecular geometries from this octahedral electron geometry. Our first molecular geometry is called an octahedral molecular geometry, the same as its electron geometry. And the reason for that is all 6 pairs of electrons around the central atom are bonding pairs of electrons. So let's look at a model of what an octahedral molecular geometry would look like. We have our central atom in red in our model, and then we've got our bonded atoms to that central atom in yellow. We've got 6 bonding atoms to our central atom. So there are 6 bonding pairs of electrons around the central atom. There are no lone pairs. And if we were to look, we've kind of got 4 sides on the top like a pyramid and 4 sides on the bottom like a pyramid, and that's where that octahedral name comes from. So if we have 6 pairs around the central atom and all 6 pairs are bonding pairs of electrons, our molecular geometry is referred to as an octahedral molecular geometry. Now let's replace one of the bonding pairs of electrons with a lone pair of electrons. We still have 6 pairs of electrons around the central atom, so it's an octahedral electron geometry. But those lone pairs of electrons are going to fill up space around the central atom, and they're going to give us a different molecular geometry. When we've got 5 bonding pairs of electrons and 1 lone pair of electrons around the central atom, our shape is referred to as square pyramidal. So if we look at this model here, we've got 6 pairs of electrons around that red central atom. But we've replaced one of the bonding pairs of electrons with a lone pair of electrons, and that's what that blue space down on the bottom of our model represents, that lone pair of electrons that isn't bonding to another atom. We've got 5 atoms bonded to our central atom, so we've got 5 bonding pairs of electrons, and the shape of the molecule is going to be square pyramidal. And kind of literally, if you look at it, you've got a square along the bottom, and it kind of looks a little bit like a pyramid along the top. So if we've got 6 pairs of electrons around the central atom, and 5 are our bonding pairs, 1 is a lone pair, our molecular geometry will be square pyramidal. Now we're going to replace another bonding pair of electrons with a lone pair of electrons. We're going to look at a molecular structure that has 4 bonding pairs and 2 lone pairs of electrons around the central atom. There's still 6 pairs of electrons around the central atom, so our electron geometry is octahedral, but now we're going to have a different shape. Our shape is going to be referred to as square planar. So if we look at this model here, we've got 6 pairs of electrons around the central atom. Above and below that central atom are lone pairs of electrons which take up space in the molecule. And around the middle we have 4 bonding pairs of electrons which are bonded to other atoms. That's going to give us a square planar arrangement. Now we're going to look at electron geometries that involve 5 pairs of electrons around the central atom. When we have 5 pairs of electrons around the central atom, the electron geometry is referred to as trigonal bipyramidal. And think about that. Tri means 3, bi means 2, so there's our 5 pairs of electrons around the central atom. Now, if our bonding pairs of electrons are all the electrons we have around the central atom, our electron geometry and our molecular geometry are called the same thing. So if we have 5 bonding pairs of electrons and no lone pairs of electrons around the central atom, our molecular geometry is referred to as trigonal bipyramidal. So in our model here, we've got our central atom, there are 5 bonding pairs of electrons off of that central atom. That's going to give us a trigonal bipyramidal arrangement. If we look kind of along the middle, we've got 3 atoms, so there's our trigonal. And then there's kind of a pyramid on top and a pyramid on the bottom, so that's going to give us that bipyramidal part. So 5 bonding pairs of electrons and no lone pairs of electrons around a central atom will give us a molecular geometry called trigonal bipyramidal. Now, if we remove one of the bonding pairs of electrons from that trigonal bipyramidal electron geometry and replace it with a lone pair of electrons, we're going to have what's referred to as a seesaw shape. So there are 5 pairs of electrons around the central atom. 4 are bonding pairs, 1 is lone pair, and we're going to have a seesaw shape. So when we look at this model, we've got our central atom. There are 4 bonding pairs of electrons and 1 lone pair of electron taking space up around that molecule, and that gives us a seesaw shape. Now when you look at that, you can't really imagine what the seesaw shape looks like. So imagine this. We're going to take this particular model that we have and we're going to turn it on its side. We're going to take those 2 bonding pairs of electrons that are kind of spinning around the center of this particular model. We're going to flip it down and put those on the table. From there then, the 2 atoms that are not moving can kind of move up and down like a seesaw. And that's where that name seesaw shape comes from for our molecular geometry. Removing 1 more bonding pair of electrons and replacing it with a lone pair of electrons in a trigonal bipyramidal electron geometry will give us a T-shaped molecule. So if we have 3 bonding pairs of electrons and 2 lone pairs of electrons around our central atom, our electron geometry will be trigonal bipyramidal. Our molecular geometry will be T-shaped. So if we look at our model here, we have our 3 bonding pairs of electrons, our 2 lone pairs of electrons taking up space in that model, and that gives us a T-shaped molecular geometry. We can remove 1 more bonding pair of electrons and replace it with a lone pair of electrons in our trigonal bipyramidal electron geometry. And when we do that, that will give us a molecular geometry that's linear. So here's our model of a linear molecular geometry. Notice that there are 5 pairs of electrons around the central atom. That gives us the trigonal bipyramidal electron geometry. But in this particular shape, 3 lone pairs of electrons and 2 bonding pairs of electrons are going to give us a molecular geometry which is referred to as linear. And when we look, all of the molecules are in a line. Our next electron geometry is called tetrahedral. And we know that when we play our Tetris games on our cell phones or our calculators, we're looking at a game where all of the pieces that we manipulate have 4 boxes in them. The term tetra means 4. So a tetrahedral electron geometry will have 4 pairs of electrons around its central atom, and depending on whether those pairs of electrons are bonding or lone pairs will determine what the molecular geometry is. If all 4 of our pairs of electrons around the central atom are bonding pairs of electrons, our electron geometry and molecular geometry will be the same, so in this case it will be tetrahedral. Now when we look at the tetrahedral model, we've got the central atom in red, we've got 4 bonding pairs of electrons, and they're going to equally distribute themselves throughout space. So we're going to get a 3-dimensional model, which is what they're trying to show in this particular model, where we're going to have a tetrahedral arrangement. If we remove a bonding pair of electrons and replace it with a lone pair of electrons in our tetrahedral electron geometry, we end up with what's referred to as a trigonal pyramidal molecular geometry. In this particular model, there are 4 pairs of electrons around the central atom, 3 are bonding pairs, 1 is a lone pair of electrons. That lone pair of electrons is going to occupy space in the molecule, where those bonding pairs of electrons are going to be pushed a little bit closer to each other and give us a pyramidal type shape. And since there are 3 atoms, we get our trigonal pyramidal shape for our molecular geometry. If we remove another bonding pair of electrons in our trigonal or our tetrahedral electron geometry, and we have two bonding pairs of electrons and two lone pairs of electrons, our shape is now referred to as bent. So if we look at this model, there are four pairs of electrons around the central atom, two are bonding pairs, two are lone pairs. We're not going to see those electrons, they just occupy space. So if we look at the atoms and their arrangement in that molecule, we're going to get a bent molecular geometry. Now let's look at an electron geometry that involves three pairs of electrons around the central atom. When we have three pairs of electrons around the central atom, our electron geometry is referred to as trigonal planar. And again, if all the pairs of electrons are bonding pairs of electrons, the electron geometry and the molecular geometry are the same. So we're going to look at a molecular geometry that's referred to as trigonal planar. When we look at a trigonal planar molecular geometry, we've got a central atom, three bonding pairs of electrons off of that central atom, and there are no lone pairs of electrons in that central atom. Therefore, all of the atoms are going to be along the same plane, and we would call it trigonal planar for our molecular geometry, as well as our electron geometry. If we look at a trigonal planar molecular geometry or electron geometry, where we remove one of the bonding pairs of electrons and make it a lone pair of electrons, now we're looking at a molecular geometry referred to as bent. And when we look at a bent molecular geometry, again, we're going to have three pairs of electrons around the central atom. There's our trigonal planar. One pair is a lone pair of electrons taking up space. Two are bonding pairs of electrons, and our molecular geometry is referred to as a bent shape or bent molecular geometry. Our last electron geometry is referred to as a linear electron geometry, and that's where we have two pairs of electrons around the central atom. And when both pairs are bonding pairs of electrons, we're looking at a linear molecular geometry. And when we look at this linear molecular geometry, notice that there are no lone pairs of electrons around the central atom taking up space, so all of the atoms in that molecule are going to line themselves up in a line, or a linear molecular geometry.